The Fukushima Renewable Energy Institute of the National Institute of Advanced Industrial Science and Technology, or FREA, was established in April 2014 with two missions: to become a global innovation hub for renewable energy and to help revitalize areas affected by the Great East Japan earthquake by developing new industrial and human resources. 5 years since its establishment, promising results are emerging from a broad range of experiments and revitalization efforts. Japan's 2018 Strategic Energy Plan includes the use of renewable energy as an economical, sustainable, and major source of decarbonized power, which makes evident the increasing importance of renewable energy R&D. Let's take a look at the strategies and achievements of FREA, the Fukushima Renewable Energy Institute, a hub of innovative renewable energy research. FREA is situated atop a hill in Koriyama City, near the center of Fukushima Prefecture. The facility generates and uses renewable energy, proving its viability. FREA has some of the largest research facility infrastructure in the country and superior environmental performance. At FREA, some 400 facility staff and international researchers collaborate with their cohorts around the world to conduct cutting-edge research in 7 different fields: geothermal, shallow geothermal and hydrogeology, hydrogen carriers, hydrogen and heat utilization systems, photovoltaic, wind power, and energy networks. Renewable energy research at FREA can be classified into 3 categories: reducing the cost and improving the efficiency of renewable energy, distribution of information about renewable energy research and development, and system integration facilitating the implementation of renewable energy. First, a look at research results on reducing the cost and improving the efficiency of renewable energy. Photovoltaics converts solar energy into electricity. The conversion efficiency of typical current solar cells is about 20%. Improving PV efficiency is a key issue. FREA has achieved a conversion efficiency of 27.7% with multi-junction solar cells consisting of gallium arsenide-based and crystalline silicon-based solar cells. Since multi-junction solar cells can use wide solar spectra more efficiently than crystalline silicon solar cells, they can achieve higher efficiencies. This multi-junction solar cell was made possible by using SmartStack, a bonding technology featuring different types of cells using metal nanoparticle arrays. By applying an ion implementation technique with a newly developed stencil mask, FREA has successfully formed a diffusion layer with a more uniform junction depth. This technology allows the fabrication of high-efficiency solar cells with far fewer steps.
効率が 30% を超えるような新しい概念の太陽電池の創出を通して太陽電池の持続的な発展に寄与していきたいと考えています。
At FREA, research is underway on remote sensing measurement technology for wind forecasting. LiDAR is the key. LiDAR is a remote sensing device for measuring wind speed and direction using laser beams. Stable winds at sea are now being recognized as an ideal source of wind power. FREA is using LiDAR to conduct R&D in assessing offshore winds. The latest development is a remote offshore wind measurement method using 3D LiDAR. In current field experiments, 2 3D LiDARs are set up along the coast, and laser beams are directed at a wind observation buoy 2.5 kilometers offshore. Data collected from the buoy and estimations made from LiDAR data are compared. Using LiDAR data, this research has made it possible to estimate offshore wind speeds to within a 5% margin of error.
このライダーを最大限活用して今後の洋上風力発電の本格的な開発・普及に向けた研究を推進します。
Complementing the sun and the wind is another source of renewable energy, geothermal energy. Unlike solar and wind power, geothermal power is firm and is thus being recognized as a potential source of base load power. To optimize the recharging of water into geothermal reservoirs for sustainable steam production, FREA is monitoring the micro-earthquake activity that occurs during these injections at the Yanaizu Nishiyama geothermal field in Okuaizu. The underground fluid flow is visualized. To allow geothermal power generation and hot spring use to coexist, FREA has developed a continual hot spring quality monitoring system. By digitizing data such as hot spring flow rates and temperature, we aim to scientifically explain the relationship between geothermal power and hot springs. Developments in supercritical geothermal resources will pave the way for the use of geothermal energy. Supercritical geothermal power generation uses thermal energy from magma 3 to 5 kilometers underground. FREA has created a supercritical geothermal system model of the Tohoku region. Based on this model, power generation simulations have shown that, in some cases, over 100 megawatts of power can be generated at one supercritical rock mass.
地熱の適正利用という言葉をキーワードに、地下や社会の状態に合わせて地熱を適正に開発するというための研究開発を行っています。
FREA research is underway on ground source heat pump systems, an energy-saving technology that uses subsurface heat, which stays constant all year long. FREA has conducted geological and hydrological surveys at various locations in the Tohoku region, and based on data collected, established a potential assessment method for GSHP systems. Using hydrogeological data, we constructed a regional-scale groundwater flow and heat transport model to simulate ground source heat pump operations. We are compiling GSHP suitability maps. In addition, FREA is evaluating GSHP systems and operation methods appropriate for regional hydrogeological characteristics. For example, we evaluated this tank-type ground heat exchanger. FREA is also introducing GSHP systems in Southeast Asia, conducting demonstration tests in cooperation with governmental and academic institutions in Thailand, Vietnam, and Indonesia.
地中熱利用システムはシンプルでローコストなシステムですが、その省エネ効果の大きいのが特徴です。地域の導入適地の分かるポテンシャルマップと地域の地下水環境を活用したさまざまな熱交換技術の開発によってその利用の幅を広げていきます。
FREA has also been working to improve the efficiency of water electrolysis by developing electrolysis control technology that can adjust the number of electrolysis cells in operation according to solar cell output. We've succeeded in converting 15% of the solar energy collected in one day into hydrogen. The hydrogen generated is supplied to Japan's first renewables-powered mobile commercial hydrogen station. Metal hydrides can be safely used as a hydrogen storage medium. Metal hydrides are alloys that can absorb 1,000 times their volume in hydrogen and desorb the hydrogen when heated. We are studying energy systems that integrate these technologies with the goal of using hydrogen to supply electricity and heat to buildings and thereby reduce emissions to zero. Electricity from solar cells can be efficiently used to conduct water electrolysis to produce hydrogen. The hydrogen is then stored in metal hydrides. This hydrogen can be desorbed when needed and converted by fuel cells into electricity. Short-term surplus electricity can be stored in batteries. The system uses tanks filled with metal hydrides. The metal hydrides are safe, non-hazardous, common metal alloys developed by FREA.
水電解、水素吸蔵合金を使った水素貯蔵、燃料電池、蓄電池などの装置を組み合わせ、 電気熱需要に合わせた運用を目指し、付加価値の高いシステムを開発します。
FREA is researching hydrogen energy carriers for the storage and transportation of hydrogen made from surplus renewable power. Hydrogen is the ideal medium for the long-term storage of massive amounts of renewable electricity. Hydrogen energy carriers make hydrogen safer to store and use. Hydrogen energy carriers such as organic chemical hydrides and ammonia reduce hydrogen gas volume to less than 1/500th and 1/1300th, respectively. FREA is the first in Japan to operate an ammonia synthesis demonstration plant using renewable energy-derived hydrogen. FREA has recently developed a catalyst that remains active in a broad range of conditions. Using this catalyst, we developed a new ammonia synthesis process suitable for renewable hydrogen at low temperature and pressure.
この実証試験の成功により、再生可能エネルギーをより効率的に水素およびアンモニアとして貯蔵し利用する技術の開発に貢献いたします。
To efficiently use massive amounts of electricity generated by renewables, smooth integration with existing power grid systems is essential. There are concerns that intensive, large-scale introduction of electricity generated by renewable sources could result in frequency and voltage fluctuations in the grid. Inverters are key to maintaining grid stability with the use of renewable electricity from intermittent sources. Inverters not only convert the direct current electricity generated by photovoltaics and wind into alternating current, they can also stabilize voltage and frequency. FREA is advancing R&D of smart inverters, vital to expanded use of renewably generated electricity in the power grid. Smart inverters not only have the potential to autonomously control power output with intermittent renewables, but also to connect with information networks to proactively support the power grid. FREA implemented automatic testing procedures for such smart inverters, helping to reduce test times by 80%. Developed by FREA, the SORA grid is a simulation tool that can analyze the effectiveness of smart inverter functions. The SORA grid is a tool for verifying grid support functions to be implemented in smart inverters and for power flow calculation in a grid with high penetration of distributed energy resources.
次世代型パワーコンディショナーは電力ネットワークを草の根から変えていきます。次世代型パワーコンディショナーで実現するインテリジェントな分散電源はインターネットとつながり電力ネットワークに新しいサービスを提供します。
To conduct experiments on and analysis of large-scale inverters, FREA established the Smart System Research Facility, the first of its kind in Japan. The facility is used as a global standardization platform in R&D and certification for compliance testing. For development of new products and their international standard certification, we conduct grid connection testing, safety and reliability testing, electromagnetic environmental compatibility testing, and system performance testing. At the Grid Connection Testing Facility, we conduct tests on required functions for the grid connection of distributed power, such as solar cells. The Distributed Power Supply Simulator is capable of supplying a maximum of 3 megawatts, 1,000 volts. Varied output can be simulated according to various conditions. The Grid Simulator is capable of supplying a maximum of 5 megawatts. Voltage and frequency can be configured to any desired value, enabling the simulation of any power grid around the world. At the Safety and Reliability Testing Facility, we simulate actual environments, conducting high-temperature acceleration and heat cycle tests to evaluate long-term reliability, and safety tests, such as surge voltage. This is an electromagnetic environmental compatibility testing facility. At the System Performance Testing Facility, distributed power can be connected with inverters to operate as one system, allowing us to conduct various system performance tests. One of our key goals is helping with revitalization efforts in Fukushima, Miyagi, and Iwate, the prefectures affected by the Great East Japan earthquake. We support the SEED Support Program, promoting renewable energy technologies invented here. Over 5 years, the SEED Support Program has worked on over 100 research projects and achieved substantial results. The program has created new industries in the disaster-affected areas. Some projects have been commercialized and received awards. With the goal of using renewable energy as a major power source for Japan, FREA will deepen cooperative efforts with both domestic and international research institutes and with regional communities, and build on innovative renewable energy technologies from Fukushima. More exciting achievements lie ahead.